Hello everybody. Hi guys, am I audible and visible? Can you all see me and hear me? Yes, I am audible and visible. So as I always say, Namaskara everyone. Andariki Namaskaram, Ellargu Swagatam, and a very warm welcome or Vanakkam to Vedantu JEE English channel. This is me, your master teacher, Nabamita ji, and today we are here to complete our equilibrium. Yes, when I say equilibrium, we will be completing both chemical as well as ionic equilibrium. So guys, please stay till the end of the session if you want to be a master in chemical and as well as ionic equilibrium. We will be doing very little problem today since it is 2 chapters. It will take me at least 3.5 hours minimum to 4 hours maybe. So once now I have started the session, it's 4 o'clock. The class will probably go on till 8 o'clock everybody. So all the other students who come in the chat box and when they ask you that ma'am, till what time will the class go on? Till what time will the class go on? Please tell them that it will go on till 7:30 or 8 o'clock. Alright everybody. Yes, hi Lakshmi, hi Unknown, hi Jeevan, hi very good evening. Hi Suleha, Sidhu, Rocker, Akshay, yay, very good evening guys, very good evening. Alright, now today's session is going to be very knowledge heavy, so I'm not going to take a look at the chat box much. You want to chat, you can go ahead and chat everybody. If somebody has a doubt, you all can go ahead and solve it for somebody else. Whenever I look at it, if I happen to see some doubts, I'll take it. Otherwise, like I said, I will be looking at the chat box very little today. Okay? Yes, everyone. Okay, so shall we start with the session? Before I start with the session, hi Rasana, Vemishetty, hi Supriya, hello Anurag. Yes, so Supriya, then I have some more students who are here. That is Mani was there yesterday. So Mani, Supriya, Tanishka, you guys please try and control the chat box and talk to the other students and make sure that they are also clearing their doubts, because I know that you all have studied a little too much and that's why I'm giving you this opportunity. Alright everybody, yes. So quickly before I start with the session everyone, let me tell you that guess what everybody? Guess what guys? Your master teachers are going to be in your city everybody. So let me know how many of you are excited for this, because I really am guys. I really am excited. I wish I could be also one of those teachers who could come to your city, but I think that will happen very soon. I will also be visiting the city. But right now, Harsh Priyam sir, Pulkit Jain sir, who is the founder, who is one of the co-founder of Vedantu, and your beloved, your 9th and 10th teacher, somebody who helped you, clearing your 10th exam, that is Abhishek KR sir, they are all going to be there in your city. So let me tell you everybody that March 17th they are going to be in Bhubaneswar guys. Okay, March 17th they're going to be in Bhubaneswar. Apart from that, March 23rd they are going to be in Janakpuri, Delhi, if you can see. Then they're going to be March 21, they are going to be in Pune everyone, and on March 31st they are going to be in Patna. So how many of you are excited for this guys? How many of you are excited for this? Because I really am. And by the way, let me tell you once again everybody that I am going to tell you about Vedantu's, I'm going to tell you quickly about Vedantu Learning Center. Yes, because why? We have highest personal attention, which will definitely make sure that you get success. We are in your city. There are a lot of states and lot of cities that we have covered already. In Kerala, you guys have not filled the form everyone. So if you want us to be there in Kerala, then you have to fill the form. Let us know that you guys are also waiting for us. And Tamil Nadu, we have so many centers. So all the Tamilians, we know that your J or your NEET is going to be Jujupi. Yes, everybody. Apart from that, we have centers in Punjab, we have centers in Rajasthan, we have center in Karnataka, in Maharashtra. So in many places, everybody, I hope that you all are very excited, because we really are. We get to travel and we get to, meet you guys. All these while we were teaching you in front of the camera only, but now we are going to be there in front of you physically. Yes. So here you will get dedicated academic mentor, You will be getting a smart clicker for every student in the class. Yes, and there will be three-way doubt solving. Doubt is something that we really take care, because we feel that once you have a potential of doubt, then you do not go forward, right? You keep thinking about the doubt that you had. That is why we make sure that your doubts are definitely getting, cleared. Okay, you will get quality teachers, you will get great content, and you will be getting rigorous test practices, because we have 3 different kind of tests that happens regularly, almost every 1 or 2 weeks, everybody. And last but not the least, one of the best thing that we have here is that actually differentiates from everybody else in the market, from every other edtech, from every other institution, that is the guaranteed improvement in marks, otherwise you get your money back. We have Vedantu improvement promise, that is VIP. So all the students, if you do not get your marks, if you do not get to improve your marks, you get the money back. And by the way, another best thing that we have done is that you get a regular parents teachers meeting, everyone. Your parents are the one who are paying the fees, and that is why we do not want to keep them in the under the lead sky and thinking that, oh, they do not know what is happening with their kids, right? So yes, your parents will get to know how their students are performing, how their kids are performing in the class, in the test, in every which way. So we take care of these many things, and here are the Vedantu Learning Center programs. There are different programs in different places. If you want, you can definitely just fill up the form that is there in the description box, and our team will definitely help you with it. And now, my dear students, without much further ado, let us start with our session. We are starting with equilibrium, that is chemical as well as ionic, everyone. So here is my note. So we are going to start with what really is equilibrium. What do we understand when we say that something is in equilibrium? Have you guys seen those birds, those the eagle kind of birds that you could keep in your finger, keep on your finger, and it would just get balanced? Have you noticed those kind of birds, everybody? Yes. Have you noticed, guys? Have you ever used those kind of things? Yeah, you must have, right? You must have, isn't it? Yes, you must have. Have you guys done that? Those eagle kind of bird that you can balance. Exactly. You know what? That is also sort of an equilibrium, but that is an equilibrium that is related to physics. But today we are going to talk about chemistry equilibrium. So equilibrium is that state where all the opposing forces, okay, all the opposing factors, they are in a state of balance. That means nobody is trying to poke the other one, or they have poked each other so much that now they're like, bro, let's be in peace and let's be stable, right? So that's what they have done. Yes, and that is your equilibrium. Now equilibrium can be static or it can be dynamic. How static and how dynamic? Look at this, guys. Look at this. See this girl, she tries to pull the donkey, and at certain point they are both not moving. Do you notice, everybody? At a certain point they're both not moving. They completely freeze. See, they pull and then they become look at that. Yes. So this is static equilibrium. That means that they have reached a position where both of them are not disturbing each other and they are in a static state. Getting it, everybody? Yes, this is clear. So that is a static equilibrium. Now look at this, everybody. So yesterday I gave you this example. Do you remember? This is dynamic equilibrium. See, the kid or the cartoon is moving upwards, but because the escalator is coming downwards, it feels like there is no change. But actually, there is a change. It is dynamic in nature. Things are changing, but you do not get to see it. You are not able to understand. For example, I don't know, do you do this in your washing machine? Because I have done it. And I'm really bad at the household chores, I can't do that. So what I've done is, one day I started the washing machine and then I forgot that the water was going on and on. Yes, okay, Bangalore has water crisis, so please do not go and tell this to police. I've done this long back, not now, okay? Not now. I don't do this now. So otherwise I'll be fined with 5,000 rupees. But let me tell you, so what happened was, I switched on the, inlet water for the washing machine, and it got filled, right? Once it got filled, then what happens? The outlet gets switched on. So the amount of water that is going out and the amount of water that is getting in, it's equal. So I kept watching and I'm not able to understand. I was not able to understand that, from where is the water coming if the water level is the same? So you get it? There was dynamic, it was changing. There was water that was coming in and the water that was going out through the outlet. But because it was equal amount, I could not figure out that why is the water not getting decreased? The water was at the same level, right? I was not able to understand that. Later on, I realized that, oh, this is what happened. So that is your dynamic equilibrium. So guys, are we clear with that, everybody? Yes. Are we clear with what is static equilibrium and what is dynamic equilibrium? Everybody, are we clear with that? Yes. I hope that till here nobody has any doubt. Does anybody has any doubt till here, guys? Does anybody have any doubt till here? I hope so not. Yes? Nobody? Okay. Now, so there are different types of reaction. In this chapter, when we are reading, yes, when we are studying in this chapter, we get to see that there are different types of reactions that we come across, right? And these type of reactions that we have classified them, or we have grouped them into two different types, it is based on the physical state only. Solely on physical state, we have differentiated the reactions in two different groups. Number one is your homogeneous reaction, where you see that all the reactants and the products, they are all in the same phase, bachos. All of them are in the same phase here, okay? So you have nitrogen is in gaseous phase, hydrogen in gaseous phase, and even the ammonia that you are producing, that is also in gaseous phase. So that is your homogeneous mixture, okay? Not homogeneous mixture, homogeneous reaction. That is a homogeneous reaction. Now coming to heterogeneous reaction, you get to see that the reactants and the products, they are in two or more phases. Look at this. Zn. Zinc here is in solid form, everyone. Do you notice this, everybody? Zinc here is in solid form. Carbon dioxide here, right here, it is in gaseous state. And then you again see that zinc oxide, ZNO, it is in solid state. And carbon monoxide, once again, my dear student, it is in gaseous phase. So we see that they are in two different phases. The reactants as well as the products are in different phases. Hence, this is your heterogeneous reaction. Am I clear? Am I clear, everybody? Yes. Am I clear, guys? Am I clear? So I'm hoping perhaps there is no doubt for you all, right? Perhaps till here nobody has any doubt, okay? Perhaps till here nobody has any doubt. Homogeneous reaction, once again, bacha, take a look at it. Homogeneous reaction is where all the reactants and the products, they are all in the same phase. So yes, N2, nitrogen in gaseous, dinitrogen in gaseous, dihydrogen in gaseous phase, as well as ammonia is in gaseous phase. And this is also Haber's process that we will be studying. Yes, everybody. After equilibrium, that I don't know, but we will see. Okay, after equilibrium, I think we're gonna do what were we doing? Tomorrow we are doing a 100 to 100 questions ka session, right? All of us together, we will be doing a 100 to 100 question, 100 to 150 question, most important 100 150 question, because that's very important. We are doing a lot of theory. If you do not practice the questions, you will be forgetting everything, right? After that, I'll be doing DNF block and coordination compound. Important hai. And in inorganic, these are the most important chapters, so I'll be doing that. And then we will also be doing P block, so that we are done with our inorganic. After that, no tension about inorganic, right? We will do that. Then we are going to do maybe we will do redox and thermodynamics together. And we will do structure of atom, because structure of atom also had a lot of questions, so that's why I do not want to miss out on structure of atom. Is that okay? This is the problem. Okay? So till here nobody has any doubt, am I right? Till here nobody has any doubt whatsoever, right? Everybody? Yes? Great. Okay. So moving on from here, now we go up to reversible reactions and we get to irreversible reaction, and this is based on direction, everyone. Have a look at it, guys. Have a look at it. Do you notice? This is based on direction. See, the previous one was based on physical state. This is based on direction. This is based on direction. So we have a reversible reaction. In this type of chemical reaction, what happens? The products, they combine and they get converted to the product. Yes, what happens? The reactants, they combine, they get converted to the product, and the products can get back to the reactant as well. And here you have an example. See, you have dihydrogen plus you have iodine, which is forming 2HI. That is 2 moles of HI, hydrogen iodide here, right, everybody? Make sense? Nonsense, everyone? Yes, great. Okay. Then you have processes which are this kind of processes, right? What they do is they move in forward as well as in backward direction. That means they proceed. What have I written here? If you are not able to understand my handwriting, which is actually understandable. I know my handwriting is not very good, but you know, I am too old to change my ways right now. You can give me a cursive handwriting book and I can try, but surely it has not helped me till now, so I doubt that aage chal ke bhi it is going to help me. But any which ways, I'm just going to tell you here that this means that it proceeds in forward as well as backward direction, everybody. Yes, this is in forward as well as in backward direction. Yes, notes maker, we have thought about it. We will start with it very soon. But bacha, please focus in the today's session right now. Okay? Please don't disturb and spam the session. Yes, we have thought about it. We will do it for 2025 students. Very soon we will be doing something. Right now, please focus here. Okay? So this reversible reaction, they attain equilibrium. I think that is obviously right. Yes, if something is formed, okay, let's say bacha, that I take a chalk and I completely make it into a powder. I completely have made it into a powder. And then if I ask you, make this powder into chalk again, no. You will definitely scold me. You will be like, this mad lady is coming here and asking us to make from powder. She is asking us to make chalk, right? Yes. Isn't it, everybody? Very good. So do you think that process can be in equilibrium? Every time I ask you to bring it back to the reactant, you are going to scold me. For that process to come to equilibrium, very difficult. Very difficult. So that means we need a reversible reaction. That, basically like wetting your clothes. You wash your clothes, dirty it, you wash your clothes, you dirty it, you wash your clothes, you dirty it. That's a reversible process. That can get into an equilibrium where it is half wet, where it is, half dirty, right? Yeah, correct. Okay. But here is irreversible process where the products, they cannot be converted back into the reactants. For example, if zinc reacts with sulfuric acid, it forms ZnSO4, that is zinc sulfate, plus it forms hydrogen gas. Okay, in these kind of reaction, it proceeds only in the forward direction. This reaction cannot happen. Are you guys understanding? This reaction cannot happen. The backward reaction cannot happen at all. Okay, full hand. And these kind of reactions, that is the irreversible reaction, they do not attain equilibrium. Clear hai, everybody? Then we come across another type of reaction which is based on speed. Yes, based on speed, you have fast reaction and you have slow reaction. The fast reactions, they are generally in ionic nature. Generally, the fast reaction that you see, for example, hydrochloric acid plus sodium hydroxide, which is a base, then they form NaCl plus H2O. These are ionic in nature, right? These are ionic in nature, and we know that this is also a neutralization reaction. This is also a where one of the atom is replacing the other atom. So that is also happening here. In case of a slow reaction, we get to observe that generally these reactions, they are molecular in nature. So here you see H2, two atoms of hydrogen, that is molecule of hydrogen. I2, see, molecule of iodine, and then it is forming 2 moles of HI. So yes, this is a molecular reaction. Okay, getting it, everybody? This is a molecular in nature reaction. Okay. Then we come across reactions based on heat, and the moment we say heat, we understand that there is something that is related to exothermic reaction and endothermic reaction. What are exothermic reaction? Exothermic reaction are those where heat is evolved in a type of chemical reaction. Heat is evolved. For example, yes, the hydrochloric acid plus sodium hydroxide acid, the sodium hydroxide base reaction, if you touch the container, you will find that there is heat that is released. It is becoming hot. The container becomes hot. So that is an exothermic process, right? But when it comes to endothermic process, heat is absorbed. So cooking, when you are cooking something, what do? You have to provide the heat. The system, your pressure cooker, your kadhai, they take the heat, they absorb the heat, right? So that is your endothermic reaction, everybody. Okay, all right. So till here, I hope nobody has any doubt. Does anybody have any doubt till here? Yes, does anybody have any doubt? I hope that nobody has any doubt till here. Nobody has any doubt till here, I hope. Yes, nobody has. Very good. Yes, calcium oxide plus carbon dioxide forms CaCO3. Yes, very good, very good. You guys are giving examples on your own. Amazing, amazing. So that means that nobody has any doubt, right? Yes or no? Great. Okay. Now let us try to understand this dynamic equilibrium a little bit, because in case of chemical equilibrium, when we are talking about, so right now we are talking about chemical equilibrium, not ionic equilibrium. We will start that after some time. Okay, we will start that maybe around 6 o'clock. We will start that. Okay. So mostly what happens in a chemical equilibrium is we get to see dynamic equilibrium, right? We do not get to see static equilibrium. Static equilibrium is for different system. Here we get to see more of dynamic equilibrium. What is dynamic equilibrium? That condition of a system in which the rate of forward reaction is equal to the rate of backward reaction, my dear student. That is called as your dynamic equilibrium. And then we can dynamic equilibrium, we can divide it into two groups, that is physical equilibrium and chemical equilibrium. So when we say that, when I said that rate of forward reaction is equal to rate of backward reaction, you must be thinking that, ma'am, what do you mean? So you saw this example, H2 plus I2, what was it forming? It was forming 2HI, right? So that means that the amount or the rate at which H2 and I2 are combining, okay, the rate at which H2 and I2 are combining to form HI, that is the rate that HI is breaking down to form H2 and I2. And this, my dear student, do you know that we do not just like to call it as equation, but we actually like to call it as equilibrium. This is a chemical equilibrium. This is not a chemical equation just. Okay, it's not just a chemical equation, it is also a chemical equilibrium. So in this lesson, whenever we see this symbol, we are going to say that we have an equilibrium. We have an equilibrium. We are not going to say we have an equation. We are not going to say we have a chemical equation. We are going to say we have a chemical equilibrium. Is this understood, everybody? Yes. So I hope that till here everything is clear. Okay, till here everything is clear. Okay. Guys, somebody is telling me that, ma'am, linear equation bata de. Is linear equation there in your chemistry? Or is it in mathematics, guys? Linear equation, I don't think so. It's in chemistry. Is it in chemistry, guys? Huh? Yes, Lohit. This is absolutely important and absolutely useful for EMCAT. Please do watch it. Everything is clear, or are you telling me that you have linear equations in chemistry? You have linear equations in chemistry? Thank you so much, Supriya. So, who is it? Bong cartoon, bacha. Bong cartoon, bacha. As you can see, I'm teaching you chemistry and not mathematics. So, I don't think I'll be able to teach you linear equations. You will have to, you will have to talk to your Ninja Mam. Ninja Mam will be able to teach you linear equation, not me. Okay? Yes, and water's Sanjay, come on, yeah. You have to drink 3 to 4 liters of water. You guys don't drink or what? You guys don't drink 3 to 4 liters of water. You should. You should. So this is the secret of my clear skin, you know. I drink a lot of water. Just kidding. Okay, guys, focus back. All right, everybody. So dynamic equilibrium, we have understood. Now the two groups of dynamic equilibrium, you know, we have further divided dynamic equilibrium into physical equilibrium and chemical equilibrium. So let us understand what is physical equilibrium. In case of a physical equilibrium, you get to see that the chemistry of the substances that you are using, that does not change. Okay, in physical equilibrium, it does not involve any changes that has to do with the chemical properties of the substance, and that is called as your physical equilibrium. All right, everybody. Yes, for example, you know how solid changes to liquid, liquid changes to gas, gas can change to plasma, but you know we're not going to talk about plasma at all. You know, that's in a very different state, right? So here gas, gas gets converted back to your solid, or it can get converted into different things. So here you can see that, you know, when solid gets converted to liquid, liquid gets converted to vapor, solid gets converted to vapor, solid gets converted to a saturated solution of a solid in liquid, or a gas, you know, gets converted to a saturated solution of a gas in liquid. All of these are physical equilibrium, because right here anything that you have started with, it remains as it is. For example, if you take sugar and if you just put it in water, and then if you keep putting sugar into water, sugar into water, sugar into water, sugar into water, at certain point you will get a saturated solution. Remember that story of my eating biryani? When I eat so much biryani that I get very full, I get saturated. Here, no changes in the chemical properties is happening. So basically, if you take ice gets converted into water and water gets converted into ice. When does this happen, everybody? When does this happen? I'm pretty sure that you know that 0 degrees Celsius is the freezing point of water, as well as 0 degrees Celsius is the melting point of ice. So at 0 degrees Celsius, if you keep a lot of ice and if you think that everything will get, keep maintaining 0 degrees Celsius, keep maintaining 0 degrees Celsius, you see that as much water, as much ice that you have kept, it will be exactly the same. There will not be any change. Why? Equilibrium. So at this point, rate of melting becomes rate of freezing, and that is when you get a solid liquid equilibrium. All right, everybody? Yes. Then you have liquid vapor equilibrium. What is liquid vapor equilibrium, everybody? Rate of evaporation is equal to rate of condensation. At that point, you have liquid vapor equilibrium. For example, at 100 degrees Celsius, water can boil. That means water can evaporate. And at 100 degrees Celsius, if you remember, it is the boiling point of water. And at that point of time, it can evaporate as well. No, I think I'm saying it wrong, right? I'm saying it wrong. So basically, you have to understand that 100 degrees Celsius, no, that won't be a great example. An example of liquid vapor equilibrium. Can somebody can somebody tell me what is liquid vapor equilibrium? Any example of liquid vapor equilibrium, everybody? Because my mind is not working. So anyway, liquid vapor equilibrium, whenever this happens, that at that point of time, the rate at which evaporation is happening, that is exactly the same rate at which condensation is also happening. Finally, we have solid vapor equilibrium. Solid to vapor is sublimation. You know naphthalene. What happens to naphthalene? Naphthalene is a solid ball, isn't it? That solid ball, if you keep it somewhere else, it does not get changed to the liquid state at all, but just like that, it flies away, and it means that it has changed to its vapor form. And from vapor form, when something gets converted to solid, that process is called as deposition, sublimation, deposition, sublimation, deposition happens. And at that point of time, rate of sublimation is supposed to be equal to rate of deposition. Okay? All right. Not only that, let us also talk about dissolution of solid in liquid. This is also a dynamic equilibrium. There is a dynamic equilibrium that exists in a saturated solution. Why? Suppose you have added sugar in the solution, the saturated sugar solution that I was telling you, right? So if you add sugar to water, yes, after some time you will get to see that there are crystals of sugar that you are getting, right? There are crystals of sugar that you are adding. So if you take a glass of water and you keep adding sugar, there will be very little amount that will get dissolved, and a little amount will also start to get crystallized, and that happens in a saturated solution. That means that at this point of time, the rate of dissolution of sugar, that is the rate at which sugar is getting dissolved, is going to be equal to rate of crystallization of sugar, isn't it? Now let's talk about dissolution of gases and liquids. So everybody, you must have seen a Coca-Cola bottle. What happens in a Coca-Cola bottle? When you look at the Coca-Cola bottle, you don't really understand that there is carbon dioxide gas or not. Once you shake it madly, then you see brrr, like this, the gas is coming. Only then you understand. Otherwise, you do not get to understand. So gas is dissolved in the liquid, right? The moment you open the bottle, what happens? The moment you open the bottle, that is something that happens, isn't it? It all comes out, isn't it? And sometimes what do? Just to mess up with our friends or our siblings, we shake the bottle and then we keep it, right? I used to do this with my brother a lot. Do you guys do that too? Do you guys do that too? Or you don't? I used to do that with my brother a lot, I used to just shake the bottle and keep it like that so that he won't know. And suddenly when he comes and when he opens it, everything comes off, so he does not get to drink. So I'll be like, yay, loss and loss. Great. We used to do that. Do you guys do that too with your siblings? Siblings are supposed to be the great enemies, right? Anyway. So here what happens is the carbon dioxide gas, it comes out, right? But when the bottle is, bottle is closed, At that point of time, you get to see that dissolution of gases in liquids, that's also equilibrium. And by the way, this soda bottle, we have studied about this in the solution chapter, something named as Henry's law. How many of you remember that, guys? Henry's law, do you remember? Henry, what did he say? He said that mass of a gas dissolved in a given mass of a solvent at any temperature is proportional to the pressure of the gas above the solvent, isn't it? Yes, everybody. So that is why what happens when you release the pressure, when you decrease the pressure, the dissolution also decreases. That means that the solubility of the gas decreases, and that was given to you as P is equal to KH multiplied with C. This was known as Henry's law that we have studied in the solution chapter, everybody. Am I right, guys? Am I right here? Chalo. Now that we are done with all of these, let us understand the characteristics of physical equilibrium. You know, everything has properties, and it is important for us to learn about the properties, right? Yes, so what are the characteristics of physical equilibrium, everybody? Yes, what are the characteristics of physical equilibrium? The physical equilibrium is possible only in closed system. Didn't you see, everyone? The Coca-Cola bottle, the moment you opened it, what happened? It was no longer in equilibrium. It was no longer in equilibrium. The equilibrium that was there, we had lost it. The equilibrium that we had, we have lost it. So physical equilibrium is possible only in closed system at a given temperature. That means the moment you open the system, the external factors, they mess with the equilibrium. Is this clear, everybody? Yes. All the measurable properties of the system, they remain constant. The measurable properties, bole to pressure, volume, temperature, anything and everything, they are all in constant. Okay. Dynamic equilibrium is there, but the dynamic equilibrium is also stable. The dynamic equilibrium is not unstable. That means there is not a single force which is more predominant over the whole situation. Nobody, not a single force. All the forces that are acting here, all the forces that are opposing each other, they are at balance, and that is why the dynamic equilibrium that we have achieved here will be stable. Okay. Then the forward and the backward processes, they occur at the same rate, and that is something that we have just read about, isn't it? Yes. So till here, I hope till physical equilibrium, everybody is clear with everything. Yes, I hope that there is no doubt, guys. Is there any doubt with anybody? Is there any doubt with anybody? I really hope so, no? Because I guess that we have pretty much done everything, right? Till here, no doubt, guys. Till here, no doubt, everyone. Do you guys have doubt or what? Just a second. Yes, this is better. Nobody has any doubt? Okay, great. Yes. Great. Awesome. 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 Chalo. Moving on, everybody. Now let us start with chemical equilibrium. So once again, let us hope that this is our general equation. Okay, this is our general equation. AA plus BB forms CC plus DD. Right? And this is an equilibrium because we are using this symbol. Right? Because we are using this. How to break dynamic equilibrium? You can change any of the opposing forces, right? See what we did in the Coca-Cola bottle. What did we do in the Coca-Cola bottle? In the Coca-Cola bottle, we just opened it. The moment we opened it, what did we do? The measurable quantity, we changed it. We changed the pressure, isn't it? Exactly. So that is what you can do. The measurable conditions, the measurable things that were constant, we have changed that. The moment you change it, equilibrium, you are breaking it. Okay, Anurag? I hope that you understood. Okay. Yes, so let us suppose that this is our chemical equilibrium. This is our general equilibrium. Once again, you see that here is this symbol and this is our equilibrium symbol. So here we are saying that the rate of forward reaction is going to be equal to rate of backward reaction. Obviously, we are agreeing to it that whenever we have equilibrium, we have to do this. Right here, everybody, A, B, C, D. The small letter A, small letter B, small letter C and small letter D. What are they? They are moles. Okay, they are moles. In this chapter, we are not going to call them stoichiometric coefficient, but let's call them moles. It's one and the same, but here in this chapter, we're going to use the term moles a little more. Okay? So chemical equilibrium, it is that state in which both the reactants and the products, they are present at, yes, they are present at what, guys? They are present at concentrations which have no further tendency to change with time. That means as the time passes on, you will not see the concentration of the reactants and the products changing, everybody. That is why you must have seen the curve, right? Have you seen the curve, everybody? If you haven't seen the curve sort of looks like this, okay? The curve, the graph looks like this, everybody. So you have this, like, okay, this is product, this is for product, and you will see that for reactant it is like this, okay? This is your reactant, the orange line, this is your reactant, everyone, and this white line, this is your product. So you get to see that as time passes on, this is your time, as time goes on and on, you will see that right now both of them are at equilibrium. Product will start from zero at the initial time, product will be zero, that means product has not formed, but you have taken reactant, a lot of it, right? You have taken a lot of reactant. See, as time passes, reactant has decreased, as time passes, product has increased, right? And after some time, what happens is they both become equilibrium. Both of them become equilibrium, isn't it, everybody? Yes, yes, yes. Today I do not have the scale. Now just understand, everybody, just look at it and please understand. Okay? All right, yes, guys, chalo, moving on, everyone. Okay, now, yes, so this chemical equilibrium, they also occur only for reversible reaction. This is something that I explained it to you, right? For irreversible reaction, it is nearly impossible to attain equilibrium. How, bacha? Once you have broken something down in such small levels that you have no idea that how do you get back from there. So if you do not know how to get back from there, then how can you attain reversible process? You cannot. How can you attain equilibrium? You cannot. So that is the whole thing. Okay? Then we come across the characteristics of equilibrium state. Yes, what are the characteristics of equilibrium? But this time we are talking about chemical equilibrium. I know some of you might tell me that, but ma'am, we are done with equilibrium characteristic. No, that was for physical equilibrium. Now we're going to talk about characteristics of chemical equilibrium, everybody. So a reaction or a process, you know, chemical reaction or chemical process, one and the same, everybody. It is said to be in equilibrium when the rate of forward reaction is equal to the rate of backward reaction. This term or this sentence we will keep repeating, everybody, that rate of backward reaction is equal to rate of forward reaction. We keep saying this, okay? Then we come across at equilibrium certain properties, right? Certain properties like pressure, concentration, density, they are constant. See, Anurag bacha, now do you understand? At equilibrium, properties like pressure, concentration, density, these are constant. In fact, if you use a catalyst, okay, if you use a catalyst, it can alter the rate of the reaction, but equilibrium does not change with the introduction of catalyst. Please do remember it, put it in your mind, engrave it in your mind that if you introduce a catalyst, you will be changing the rate of the reaction. You will not be changing the equilibrium of the reaction. If it does, it's a bad catalyst. It's not supposed to be used. Okay. If temperature changes, then you will get a new equilibrium. Yes, equilibrium is exists for a particular temperature. The moment you change the temperature, you will get a new equilibrium. You will not have the same equilibrium that you had. You will get a new equilibrium. A new equilibrium will be achieved. Okay? All right, everybody. Yes. Now let us come to the point. There are more characteristics, by the way. At equilibrium, the concentration of each of the reactant and the product will become constant. See, this is the graph that I was talking about. This is the graph that I was talking about. At certain points, see, it becomes constant. Yes, the line is pretty much parallel to the x-axis. So is this line. This line is also, parallel to the x-axis. That means that at equilibrium, the concentration of each of the reactants and the products, it will become constant. Temperature and equilibrium relation. Mahesh, can you wait, bacha? What have I told you? What have I told you? Don't I tell you this? That I'll tell you all of it. But right now you have to wait. Yes, I'll come to it. You will get to see everything and anything that you have doubts with. I'll come to it. Don't worry. Imagine that this is a movie. Just keep your popcorns nearby. Grab your popcorns and keep watching the session. I promise by the end of the session, once you go back to your notes, you will be able to understand basically everything. Okay? All right. And equilibrium, it is dynamic in nature here and not static. That is what I told you. That is what I told you, everybody. What did I tell you right now? I have just told you that an equilibrium, when we are talking about chemical equilibrium, we get to see that it is not a static equilibrium, but it is a dynamic equilibrium that we have. Okay? All right. Yes. Yes, Supriya. Supriya, you know that. What does a catalyst do? The catalyst does not participate in the chemical reaction. The catalyst is only making the pathway of the reaction shorter. So yes, it is not supposed to do anything with the concentration of the reactant and the product, isn't it? A catalyst does not do anything with the reaction. It doesn't participate in the reaction itself. So that means that it is not altering the concentration, right? So that is why I am saying that the rate of reaction will be changed, but equilibrium will not get affected by the catalyst. So yes, there is your answer. Now, equilibrium, you can approach it on either side. You can approach it with either side, everybody. Either from the forward side or from the backward side, it has to be the same. Okay? What is the difference between static and dynamic equilibrium? Static equilibrium is where... Okay. Chalo. So I take my chashma box and I keep it here. This is equilibrium, you know. This is equilibrium. How is this an equilibrium? There is a normal force that is acting. There is gravity that is acting. There is, maybe there is a thrust that is acting, and there will probably be a drag force that is acting. But this is at static position. It is stationary. It is stationary. I know right now I have started to teach you physics, but yeah, do you get it? This is a static equilibrium. A dynamic equilibrium is where the change is happening, but you feel like, oh, there is no change. For example, let's say that today I'm having a birthday party. Okay, let's say that today, right now at my house, I have a birthday party, and let's say that I have asked everybody to come, to come together. Mahalakshmi, 30 years too late to tell me that to change my handwriting, can't really do it right now. Can't really do it, seriously. Can't. I wish I could, but yeah. 30 years too late for me to change my handwriting right now. You can probably do it, but yeah. Anyway, so everybody, 2 people are coming in, 2 people are leaving the house. Every time 2 people are coming in, 2 people are leaving the house. 2 people are coming in, 2 people are leaving the house. What will happen? Change is happening. The change in the birthday party is happening, Every time people come in, they're like, hi, and like, okay, bye, I'll see you later. Change is happening. But do you understand? You don't. Do you get to know? You get to see that when the party started, there were 10 people, and at the end of the party, there is still 10 people. But there were changes. There were changes. So that, my dear student, is a dynamic equilibrium. But static equilibrium is where things are at stationary. Things are at rest. There is no movement whatsoever. So that is your static equilibrium. Okay? Alright, what are you saying? It's unexpected. Ma'am, are you teaching in Dubai? I know, I don't think so. I'm teaching here. I don't think so. I'm teaching, yes. How does it would get constant? I am not understanding, Bacha. What is your question? First you ask me, are you teaching in Dubai Center? Then you ask me, how does it would get constant? I'm not able to understand. Sorry. Please be a little more clear. Be a little clear, but the concentration, which concentration? You have to be a little clear, bacha. Not able to understand. Where are you? I was just teaching dynamic and static equilibrium. Now you're asking me about concentration. I'm a little confused. Tanishka, Supriya, can you please check out with unexpected doubt? Yes, Tanishka, you were right. Yes, you're right. You're right. For example, okay, Tanishka, one more thing. One more of static equilibrium. Okay, so if I balance this pen here, it is an equilibrium, but this is static equilibrium, right? This is static equilibrium. Getting it? Yes. Concentration of reactant and that I know. Concentration of reactant and product only you'll be talking. Are you talking about this graph? Are you talking about this graph? What are you talking about? This graph are you talking about? If you are talking about this graph, then yes, at equilibrium, when you have achieved equilibrium, then what will happen is the concentration of each of the reactants and the products, they will become constant. Why so? Because at certain point you have achieved equilibrium. Now what is happening is the reactants are forming product, product are forming reactant, reactant forming product, product forming reactant, right? So at certain point, again, see, it is the dynamic equilibrium. Just like how in a party there are 10 people, 2 people coming in, 2 people leaving, 2 people coming in, 2 people leaving. Similarly, in this reaction, when you have attained equilibrium, reactant forming product, product forming reactant, reactant forming product, product forming reactant. So the concentration remains the same. You do not get to see that there is a change in the concentration, but changes is happening. Changes are happening, but you do not get to see it because it is, it's dynamic in nature. It is constantly changing, but you feel like, it's same. Get the thing? Sorry, bacha, I did not understand. Sorry. Now I hope that your doubt is clear. It's unexpected. Now I hope that your doubt is clear. Yes? Right? Getting it? Clear? Chalo. Okay. Last but not the least, once again, everybody, you have to understand that equilibrium is achieved in a closed system only. You cannot achieve equilibrium in an open system. Am I right, everybody? Yes. Now let me teach you, let me show you some of the reactants that we will be taking a look at in this chapter. A little too much, okay? Again and again, we will be talking about these type of reactions, okay? So you have H2 plus I2 forms 2HI, you have N2 plus 3H2 forms 2NH3, you have PCl5 that is equilibrium with PCl3 plus Cl2, you have Fe3 plus SCN minus that forms FeSCN3 plus. This is a coordinate complex. If you thought that equilibrium only is with molecular reactions, do you notice that even coordinate complexes are formed and even they are in equilibrium, everybody? Last but not the least, you also have NH4Cl that forms NH4 plus Cl minus. There are plenty of other reactions also, but these are the reactions that we will be taking a look at, oftentimes in this chapter. So I hope that till here, no doubt, everybody is clear. Perhaps no doubt. If you have doubt, let us address it right away. What are the things that we have studied? We have studied types of reaction. We have understood static dynamic equilibrium. We have studied physical equilibrium, chemical equilibrium, characteristics of physical equilibrium, characteristics of chemical equilibrium. Within 50 minutes, we have done almost 7 to 8 topics, everybody. So any doubt, guys? Any doubt, everybody? Yes. If not, then let's move on. If not that, let's move on. Okay? By the way, I also have the typed notes that I can give this to you. Okay? I also have the typed notes. Let me show you. See, here I have the typed notes also. Okay? From here you can understand. So if anybody who said that, ma'am, we cannot understand your handwriting, no worries, no problem. You will be able to understand from here, right? This is very nicely written. So study from my handwriting, whatever I have written, because it is easier to explain. But once you are done with everything, then you can go back and you can watch this. Okay? Alright, nobody has any doubt? Great, amazing, super amazing students then. Chalo. Now, let us take a look at the Haber's process, everybody. Haber was a guy, obviously. Yes, Haber was a chemist. Camphor show which type of equilibrium? Anurag, virtual slap मालूम है? मार खाओगे थोड़ा सा? है? मार खाओगे थोड़ा सा? इतना आसान सवाल पूछोगे तो जेई में कैसे बैठोगे बच्चा? हाँ? अनुराग, मैंने क्या बोला? मैंने आपको नेफ्थलीन के बारे में बोला. तो कैम्फर क्या होता है? कैम्फर भी सॉलिड होता है. That is also in solid. Solid to gas it goes, and from gas it goes to comes back to solid. Anurag, are you appearing for 2024 JEE or 2025 JEE? Yes, Anurag? In which one are you appearing for, bacha? अगर आपका JEE, if you are appearing for 2024 JEE, okay, then this is a very पिटाई खाने वाला काम, very पिटाई खाने वाला काम, ठीक है? तो pay a little more attention. 2025, अच्छा, then it is fine, बच्चा, ठीक है? Then it is fine. Then it is fine. Then you sit here. I'll explain your doubts. But Tamil, illa, Tamil tediyar. I only know jujupi stuff. ठीक है? Anyway, so Anurag, ठीक है. Okay, Supriya, Tanishka, Dhanush, Mahesh, I'll tell you guys one thing, that Anurag is your junior. Okay? Anurag is going to sit for 2025 JEE. But this equilibrium chapter is an 11th standard chapter. It's a very good thing. We must appreciate him that he is here today and he is trying to learn from today's session. Please help him with his doubt. Okay? Anurag Bacha, good, good. Very appreciative that you are sitting here in the class today and you are trying to understand a very big concept. Okay? Oh, you are also 2025. Achha, I did not know. Okay, then I will only solve your doubts. No problem. I will only solve your doubts. So keep asking your doubts. I'll solve it. No worries. Okay. All right, everybody. Now let us come to the process that is Haber's process. In Haber's process, what happened was he took nitrogen, he took hydrogen, and it formed ammonia, right? Yes. And you see that, concentration of hydrogen and concentration of nitrogen at certain point is becoming parallel to x-axis once again. Do you see? It is becoming parallel to x-axis once again. That means that the reactants concentration is getting constant. Similarly, concentration of NH3 is increasing, but at certain point you see it is also becoming parallel to x-axis. That means this is also in equilibrium. Now you know what Haber did? Haber did a very interesting job here. He did a very interesting experiment. He not only did the experiment with hydrogen, but he also did the experiment with deuterium. Deuterium is also hydrogen, I know, isotope of hydrogen, but he did it with deuterium also. And he saw that he was getting exactly the same composition, he was getting exactly the same type of reaction, just that instead of NH3, he was getting ND3. ND3 is nitrogen with deuterium 3. But he was getting it. So Haber conducted a series of reactions. See, I don't understand my own handwriting. What will you understand? कोई बात नहीं तनिष्का, you help them, ठीक है? You help them. So what I was telling you was that Haber, what he did was, he did a very interesting series of experiment at high temperature and pressure, and then he measured the amounts of ammonia, nitrogen and hydrogen at regular interval of time, and he figured out that, whoa, equilibrium exists. And then I told you that what he did was, he did not only have the reaction with hydrogen, but he also conducted the same experiment with deuterium, and he found that everything was very similar. There was equilibrium even at that point of time. Even when they reacted with deuterium, yes, there was an equilibrium. It's just that instead of NH3, he got ND3. So guys, are we clear with this? Are we clear with Haber's process? Is there any doubt related to Haber's process, everybody? Any doubt related to Haber's process, guys? Any doubt related to Haber's process? Yes? Right? Very good, Supriya. Very good. Chalo. Now guys, moving on. Thank you so much, Dhanush. Thank you so much. Thank you so much. Okay, guys. Now let us take a look at the rate of reaction. What is the rate of reaction? We kept saying that rate of forward reaction is equal to rate of backward reaction. But what is rate of reaction? We did it yesterday, guys. Chemical kinetics. Rate of reaction. What is it? Defined as the change in concentration of a reactant or product per mole in a given unit time. Wasn't that? We did that yesterday, chemical kinetics. So yes, we are going to talk a little bit about chemical kinetics here as well. So you see the reaction rates and concentration. For a reactant, what do you do? It is minus dA by dt. Yes. For products, minus dC by dt. Yes. At equilibrium, there is no net change in concentration resulting in a reaction rate of 0. So that means that minus dA by dt is equal to dC by dt is equal to 0. Because obviously equilibrium, right? So no changes. No changes. No changes at all. Yeah, no changes at all. That is why the reaction rate becomes 0. Easy peasy biryani tasty, everybody. Till here, rate of reaction, we understand that at equilibrium it's going to be 0, because the rate of change of reactants, rate of change of product is absolutely simple. It is all equal, that means 0. Right? Agreed, guys? Yes, agreed? Agreed, agreed, agreed. Clear hai, guys? Quickly, quickly, quickly. Every slide I'm asking you that are you clear with it or not? How it is 0? Okay. Bacha, rate of forward reaction is supposed to be equal to rate of backward reaction. Yesterday, when we were doing rate law, rate of reaction, how were we finding it out? Yes, there was a rate of disappearance, rate of appearance, but now I am saying that the rate of disappearance and rate of appearance is same. So at equilibrium, that means there is no net change in concentration. Obviously, there is no net change in the concentration, right? So Baba, the rate of reaction, it is based on the concentration, isn't it? So minus dA by dt, it is equal to dC by dt. What is dC? C is the product, let's say. So C in square bracket means it is the concentration of C. Both the concentration are exactly equal. That means the net change in concentration is going to be 0, isn't it? We're talking about net change in concentration, people, not net change in concentration. Mahesh, getting it? Okay? Okay. Now, my dear bachos, we come across something that is called as law of mass action. What is law of mass action? Simple. This is your mass action. So let's suppose that you have XA plus YB as your products. Then what is your rate going to be? Your rate is going to be K, A to the power X, B to the power Y. Remember yesterday I told you that yes, we will be studying law of mass action, and yes, here this part that I have written, it is the explanation, word explanation of this. I think that you can just read this. It is going to be repetitive, so I think we can move a little faster. Shall we move a little faster, everyone? Law of mass action, we know that at constant temperature, rate of chemical reaction is directly proportional to the product of the molar concentration. What are these two? These are A is molar concentration, B is molar concentration of reactants, with each concentration term raised to the power equal to the numerical coefficient. What is X and Y? X and Y are the numerical coefficient. What did you do? You raised it to the power. That's it. In the chemical equation. That's it. Easy peasy biryani tasty. Yes, everybody. Yes. Correct, everybody. Correct, everyone. Yes. So this is simple. I don't have to explain much. We have done this yesterday. Now, if I give you example, let me give you some examples. See, if we are taking, I told you, right, there will be those examples that we will be again and again studying. So see, once again, we have hydrogen plus iodine, which forms 2HI. Then what is going to be the RF? RF is rate of the forward reaction is proportional to concentration of H2 multiplied with concentration of I2. Bacha, tell me something. What do you call this? Okay, this will be called as product of the concentration of reactants, isn't it? Product of the concentration of the reactants. Please remember, because these sentences, they tend to be a little more example. Yes. Mahesh bacha, wahi na, same na. X and Y are stoichiometric coefficient, X and Y are moles. Same thing. It's the same thing. In this chapter, we will mostly call it as moles. Moles, stoichiometric coefficient, same. In the mole concept chapter also you have seen, no? Mole concept chapter, the first chapter in class 11, you have seen, isn't it? Yes. It's the same thing. Okay. Just that in this chapter, we will be talking more about X and Y. But law of mass action is similar to both chemical kinetics and this chapter. Hence, we said that stoichiometric coefficient. Yes, bacha, yes. Okay? Alright. So, what is this? This is product of the concentration of the reactant. That means that rate of forward reaction. To remove the proportionality sign, I have added a constant here, which is Kf, that is H2 concentration multiplied with I2 concentration. Now here is Rb. What is Rb? Rb is rate of backward reaction, and that is proportional to Hi raised to the power of number of moles of stoichiometric coefficient, that is 2. So here also Rb is equal to Kb multiplied with concentration of Hi square. Yes, everybody. Are we here? Are we here? Yes. How reaction concentration in RF? RF means rate of forward reaction. And RB means rate of forward reaction. Yes? Yes. How to contact you? You can contact me on Telegram channel. You can contact me on my Instagram. But again, I'm mostly available on YouTube, so you can just comment under the video. I can reply to that. Okay? Alright guys, moving on everyone. Now let us understand law of chemical equilibrium. Once again, this is going to be very simple and just like yesterday's session, that is for the reaction AA aqueous plus BB aqueous forms XX aqueous plus YY aqueous. Here what is going to be your Kc? Kc is your equilibrium constant at constant temperature. My dear students, do you remember the characteristics of equilibrium? What did I tell you? That at temperature, if you change the temperature, you will achieve a new equilibrium. That is why I am writing here Kc is equilibrium constant at constant temperature. And how are we writing Kc? Kc is equal to product of the product. See, I have just taught you, right? Product of the reactant. Here is C, X and Y. X and Y are on the product side, isn't it? X and Y are the product, isn't it? X and Y are the product, correct? Yes, so they are on the product side. That means this is product of the products raised to the moles or stoichiometric coefficient. Okay? Alright, divided by product of the reactants raised to their moles or stoichiometric coefficient. Okay? And once again at equilibrium, here we know that rate of forward reaction is equal to rate of backward reaction. Yani ki we can also say that Kf multiplied with the product of the reactants is equal to Kb multiplied with the product of the products. Everybody, are we clear? Yes? Yes, everyone? Great. Now here, this is the explanation or the word explanation of the law of chemical equilibrium. Once again, I think we can skip it because we already know this, right? Because we already know this. Now, my dear students, here are some important points, okay? Here are some important points that are very important. So let us talk about this. Which are the things that you have to remember it, okay? You have to remember this, everybody. These are very important points, okay? Actually, have I written this twice? Acha, we will come to the equilibrium, we come to the important points a little later. We will come to the important points a little later, okay? Here, let me tell you. Where did it go? Huh. Let us talk about the steps to write equilibrium constant. Okay, let us talk about how do you write equilibrium constant. Number one, what do you do? Step number one is to write the equation of the reaction. Obviously, first you will always write the chemical equation, what is happening, yes, with the number of moles, with the stoichiometric coefficient or whatever, you will write that, okay. Now, next what are you going to do? Next you are going to write product of equilibrium constant of products in the numerator, okay. In the numerator is at the top. I have just told you, everybody, product of the products are in the numerator, okay. All right, yes, okay. Next step, everybody, is write the product of equilibrium concentration of reactants in the denominator. Reactants, product of the reactants in the denominator. And here, everybody, if there is a pure solid or if there is a pure liquid, then they will have constant molar concentration, hence you will ignore them, okay. Hence you will ignore them, everybody, okay. Step number 4 is that you will raise the concentration terms to the power equal to the stoichiometric coefficient or the number of moles, everybody. So for example, if you have AgBr, which is in solid form, then you know that it will form Ag plus aqueous plus Br minus aqueous. That means that your Kc is going to be Ag plus Br minus divided, this is your Kc, right? This is your Kc. That is how you are going to write it, okay? All right. Is the concentration of solid? Yes, you are going to ignore it, okay? You are going to ignore it because they are going to be constant, okay? All right, everybody. Characteristics of equilibrium constant. Now, equilibrium constant bole to everybody, please remember what is equilibrium constant. That means that we are talking about Kc, okay? Then after that, we will also learn about the types of equilibrium constant. Yes, what did you think? Only Kc, if we learn that is enough? No, after Kc, we will learn about Kp, we will learn about Kx, we will learn about Keq, we will learn about a lot of things. But now, right now, we're going to talk about Kc, everybody. Okay? Yes. Yes, solid and liquid have constant concentration. Yes, so it is taken as one and it is ignored. So yes, all the three of them. Thank you so much, Tanishka. You are articulating whatever I'm trying to say very well. Thank you so much. Okay. So guys, here what are the things that we have? For Kc, we know that equilibrium constant is applicable only at equilibrium state. It is independent of initial concentration. Does not matter what is the initial concentration you are taking, equilibrium constant will not get affected at all. Okay? Yes, it has definite values for every chemical reaction at a particular temperature. You must be thinking, no, but why are we calling it a constant if it has a definite value for every chemical reaction? We will come to that. I will tell you those important points that I wanted to tell you. I'll tell you that also. Then you will see that the equilibrium constant value is independent of the catalyst. See, once again we have come to the same thing, that the catalyst does not do anything with it. Okay, different units for different reaction. Just like yesterday, you know, second order, first order, you have different units. Here also you will have different units. Now let us take a look at it. That how come they have a different unit? Suppose you have the reaction, your general reaction is AA plus BB. It should be BB, sorry. Okay, it should be BB, this is BB, then you have CC and DD, right? It forms. So Kc is supposedly C to the power C, D to the power D divided by A to the power A, B to the power B, right? This is how we write Kc, correct? This is how we write Kc. Now, all of these, the terms that are in the numerator, what are they? Concentration. The terms that are in the denominator, they are also concentration. What is the unit for concentration? It's mole per liter. Now, mole per liter, that means that as per this, okay, as per this, we will also have to add C plus D because they are exponential term, and that's the property of the exponents, that if they are there, then we will be adding them. So we are going to do C plus D. Similarly, for the denominator, it is going to be mole by liter, mole per liter. But here we will be raising it to the terms A plus B. Yes, we will be adding those exponents, but look at this, what happens. Here Kc becomes mole per liter. So let's take mole per liter common. We have taken mole per liter common. Then it becomes C plus D minus A plus B. Minus A plus B. That means all together we can write that mole per liter, and then it will depend on delta N here, delta N. So mota, or that means the gist of the story is that the unit will depend on the number of moles or the stoichiometric coefficient of the reaction. Guys, am I making sense, everybody? You tell me. So if a number of moles of product is same as number of moles of reactant, then K has no unit. Why so? You will ask me that if the number of moles of reactants and products are same, Arey Baba, then what will happen? C plus D minus A plus B is equal to what? 0. Right? If you do 2 minus 2, it is equal to 0. So anything raised to the power 0 is going to be what? It is going to be, then K has no unit. Then K will have no unit. Make sense or nonsense, everybody? Make sense or nonsense? Yes or no, guys? Yes or no? Bachus, are you here with me? Are you here with me, Bachus? Yes or no? Yes. Thank you so much, Rohit. Okay. Now guys, let us come to the important points. Okay, if number of moles of product is not equal to the number of moles of reactant, then K will have certain units, and it will depend on the change in number of mole, obviously, because you are subtracting it, right? Now when addition of two equilibrium leads to another equilibrium, so let's say that you have one equilibrium which is K1, you have another equilibrium which is K2, right? Yes. So if you add the equilibrium, then what will happen? Then the product of their equilibrium will give us the equilibrium constant of the resultant equilibrium. We did not understand this, right? We did not understand this. Yes, everybody. Don't worry. I'll explain it to you right away. Just give me 2 minutes, okay? But before that, let us understand what are the different types of equilibrium. So you have Kc, you have Kp, you have Kx. What is Kc? Kc is the equilibrium constant in terms of molar concentration. Same what we have studied, that is x raised to power x, y raised to the power y divided by a raised to the power a, b raised to the power b. Kp is equilibrium constant in terms of pressure. When you have only gaseous reactants, that's when we use it. And Kx is when equilibrium constant is in terms of mole fraction, everybody. That's when we do it. Okay. Alright, everybody. This is clear, guys. Is this clear, everyone? Is this clear? Huh. Chalo, I will explain you this now. Or no, let us continue with this. Let us continue with this. I think we will come to that anyway. Huh. So now what is KEQ? KEQ, remember I told you, so there is not only Kc, Kp and Kx, but there is also KEQ. KEQ is your equilibrium constant, everybody. And this involves all the species in equilibrium. It includes solids, it includes liquids, it includes gases, it includes solvents, it includes solutions, everything. Everything, it's like an umbrella that includes everything. It represents the general equilibrium conditions, yes, where without restrictions on the state of matter. It does not care about the state of matter at all, and it will represent the general equilibrium condition, everybody. Okay. Alright, now we come across Kc. What is Kc? Kc is equilibrium constant for concentration, everyone. It includes those species which only have variable concentrations, such as gases and solutions, and that is why we are excluding solid. It excludes pure components like solids and liquid as well as solvents. Check it out, see? Exactly those things that I said. It is applicable when you are dealing with reactions that involve gases or solutions where concentration changes are significant. That means concentrations are changing and you are able to observe that concentrations are changing. It's not like, it changed but you did not get to see it. It changed, like properly, significantly it changed, okay? Then we come across Kp. What is Kp? Kp is equilibrium constant for partial pressure. That means this is definitely applicable only for reactants and products when they are in gaseous phase, right? Now, if the components in the equilibrium should be in the solution phase, then what do you do? If they are, then what will you be representing it as? You will be representing it as KPC, guys. It will not be Kp, it will not be Kc. But if you have the equilibrium and if it is in the solution phase, then you will represent it as KPC, everybody. Okay. Then we know the ideal gas scenario, which is PV is equal to nRT. That means we can write P is equal to N by V divided by RT. That means P is equal to CRT. And guys, related to this, one question had come in the JEE Mains, I think in the year 2022, if I'm not wrong. In the year 2022, there was a question wherein they did not take in the graph, they did not take they did not take NV, they did not take N by V, but they took C. And majority of the students thought C means molar concentration. Majority of the students, they thought something else and they have done a mistake. Okay, they have made a mistake in that question. So please listen to it very carefully. P, N by V. We can write N by V to be as C. Okay. And what is the unit of Kp? Unit of Kp is going to be Pascal. It can be bar. It can be atmospheric pressure. Okay. It is the same formula as for osmotic pressure. Yes, it is. It is. It is. Now, if somebody asks you, what is the relation between Kp and Kc, guys? Kp is equal to Kc multiplied with RT, and here on the top you will write delta Ng. Delta Ng is basically the difference of stoichiometric coefficient of gaseous products and reactants. Just like how we did delta N. What is delta N? We understood. Similarly, we here have delta Ng. Okay. Finally, we come across Kx, which is your equilibrium constant in terms of mole fraction, and here we understand that it is expressed using the mole fraction of reactants and products. Okay. It is done what? You express it in mole fractions of reactants and products. Useful when you have gas phase reactions where concentration of pressure data are not available, where either concentration or pressure data is not available at that point of time. Just use your kx. Okay, just use your kx. It does not have any units because we all know that mole fraction itself is dimensionless, obviously. So if mole fraction does not have dimension, how do we expect, kx to be having dimension? Okay. Now guys, let us talk about the important points and let us understand all the things that you have not understood till now. Remember that point where I said that the resultant equilibrium is going to be the product? Chalo, let's try to understand this. Okay. So if we reverse the reaction, let's say that you have a reaction where A plus B is forming C plus D. Reverse it. Now we are saying that C plus D is going to become A plus B. You know what happens? The Kc is also inverted. Suppose for A plus B forms C plus D, your Kc was supposedly 10. Maybe, perhaps it was 10. Now, for the reverse reaction, the new Kc is going to be 1 by 10, my bachus, okay? The new Kc is going to be 1 by 10, okay? Next, if the equation is divided by 2, then the Kc for the new equation is square root of K. Check it out here, see? If we take 2SO2, okay? If we take here 2SO2, everybody, check it out. 2SO2 plus O2 is forming 2SO3. Let us divide it by 2. So 2SO2, that means that if you divide it by 2, it will become SO2. O2 will become half O2 and 2SO3 will become SO3. Now, Kc for the above reaction was 25. The moment you have divided it by 2, it will become square root. So Kc, new Kc will become root over 25, which is equal to 5. Are you getting this, everybody? Yes. What about Kx? What? One line definition or difference are you asking, Tanishka? What about Kx? Told you, no. This is your Kx. Oh, sorry, it is going forward, guys. It is going forward. Sorry. What about Kx? Bole to what are you asking? I'm not able to understand, Mahesh. Can you be a little clear and tell me what are you asking? Difference. There is no difference as such, bacha. There is no difference as such. All of them are equilibrium constant. It's just that Kp is used when you have gaseous phase. Mole fraction, Kx, mole fraction is used when you have, gaseous concentration, or let's say that pressure is also not available. Yes. So at that time, whenever mole fraction is changing a lot, whenever concentration is changing a lot, that time you can use a mole fraction. That time you can use equilibrium constant with respect to mole fraction. Okay. Normally we like to use Kc because wherever we know the concentration, then we can use it, right? So normally, in general, most of the time we use Kc, but whenever you see that, acha, this is not there. There are gaseous reactants, gaseous product. You use Kp. Even after seeing that Kp has to be utilized, but you still do not have pressure related any data, then you use Kx. That's it. Okay? There is no difference as such. So guys, the some important point, these two are clear. If it is clear, moving on. Now, if the equation is multiplied by 2, then what will happen to the Kc? Then the next Kc, the new Kc will be squared. It will be squared. See, check it out. So you have taken, let's say, half NO2 plus half O2 and that forms NO. So let's say that Kc is equal to 5. Now, if you have multiplied it, see, if we multiply, it will become N2, it will become O2, and then it will become 2NO2. Sorry guys, this should not be NO. This should be N2. Okay, this should be N2. Okay, yeah. So here see what will happen. Here see your Kc square will become 5 square, that is 25. Are you getting it, everybody? Yes. Now if a reaction happens in multiple steps, it becomes a little difficult. Okay, it will impact the overall reaction. So suppose you have A to B, which is your overall reaction. Yes, the reaction that is actually forming, A is your initial thing, A is your initial reactant, B is your final product. But suppose it is not as easy as it looks like. Okay, what if A is first forming C plus D? So he will have Kp1. Okay, then what is happening is C is forming E. Let's say you have Kp2. Then you have D plus E is together forming B, which is Kp3. Now see what is happening. Yes, now see what is happening. So the actual Kp is Kp1 multiplied with Kp2 multiplied with Kp3. That means all the Kp products are going to give you Kp. Now do you understand that when I told you that resultant equilibrium constant will become the product, everybody? Yes, resultant equilibrium will become the product, everybody. So that is exactly what I meant, everyone. Okay. Yes, I'm doing equilibrium from the scratch, bacha, because I don't think that you have a session on this in this channel. That is why. Okay. It's just change in formula to find the value of the constant, but all give the same thing. Yes, Tanishka, absolutely. So Anurag, Kc, Kx and Kp, they are all equilibrium, but they have different data that will derive you this. Okay? Different data will derive you this. So it might not be the same, but you are actually trying to find the constant only. Okay, you are actually trying to find the constant only. Now everybody, let us check it out. We had some more important points, isn't it? All this, so I explained. Now nothing else is here. Nothing else is here. We're done till here. Okay. Acha, now let us understand the factors that do not influence equilibrium constant. Yes, let us understand the factors that do not influence equilibrium constant. See, concentration of reactant and products, that's not going to change the equilibrium constant. Pressure and volume, if you change, it is not going to change the equilibrium constant. Pressure of a catalyst, presence of a catalyst, sorry, not pressure, presence of a catalyst, not going to change anything. Addition of inert gas at constant pressure and volume, not gonna change it at all. But obviously, what is going to change? Let us understand that. Then what really does influence the equilibrium constant? Okay, all right. So here, everybody, I need you all to pay attention, my dear students. Here I need you all to pay attention, everybody. Are you all here with me? Are you all here with me? Here I need a 1 second, huh? And Asha, this is only the background or what? Sorry guys, extremely sorry. Just a minute. I don't have a page. Just a second, guys. Just a second. Be right there. I'm not able to add a page here. I need to add a page. Just a second, yeah? Let's finish equilibrium, no? Let's finish chemical equilibrium only, then we can do. Yes, found it. Sure. Okay. Here we are, guys. Okay, so now let us understand the factors that influence equilibrium constant. Okay, factors influencing equilibrium constant. What are the factors that do that? Number one is mode of rep. I think I did have this thing. Wait, I think I had a slide here. I think I do have a slide here. I did add it some from yeah, found it. Shall we use this? Yes? Let's use this, है ना? Then it will be easier for us. Yeah, here it is, guys. Here it is. Everybody, take a look at it. So the factors that influence the equilibrium, you have mode of representing a chemical reaction. How are you representing the chemical equilibrium? We will see the example. Stoichiometry of the reaction and temperature can change the equilibrium constant, everybody. Now look at it. Mode of representing a reaction. For reaction, let's say that we have 2HI which forms H2 plus I2. Okay. And let us suppose that the equilibrium constant here is your Kc1. Okay? Everybody check this out. Here, equilibrium constant here is Kc1. Let us suppose. Okay? Now, Kc1 is basically H2, concentration of H2 multiplied with concentration of I2 divided by concentration of the product, which is Hi raised to the power 2. Am I right? Or Hi is the reactant here. Let's say Hi is the reactant here, so raised to the power 2. Right? Now consider this to be your equation 1. If we write it in the inverse manner, guys, instead of writing 2Hi forms H2 plus I2, what if we write it as H2 plus I2 which forms 2Hi? If that is the case, then our equilibrium constant will become Kc2. That means that Kc2 will be the product, which is 2Hi. So product raised to the power 2 divided by concentration of the reactant H2 multiplied with concentration of reactant I2, which will basically 1 by Kc1. Guys, are you understanding? Guys, are you able to figure it out that what is really happening here? Yes, everybody? Are we understanding that how just the representation of the reaction can change your Kc, everybody? Okay. The stoichiometry of the reaction. For example, just like I have just explained, isn't it? See, now if you had H2 plus I2, what if you just half it? What if you take half of H2, half of I2, and if you have Hi, only if you are forming Hi, then what will happen? Your Kc2 will become Hi divided by H2 raised to the power half, I2 raised to the power half. So the moment you change the stoichiometric coefficient, it will change again, everyone. Okay? All right, everybody. Are you getting it? Oh, there is a weird thing that is happening. You know what? Let me change the view. Okay? The view settings, I'm going to change it to seamless. This is better. Okay. Yes? Alright guys, this is clear to you all. Is this clear to you all? Chalo, let us move back to our this thing. So factors not influencing equilibrium constant, factors affecting equilibrium constant. I hope that we have understood all of it. Okay. What is the effect of temperature on equilibrium constant? If you increase the temperature, we have seen that it favors exothermic processes. It favors exothermic reaction. If you increase the temperature for any, it favors endothermic process, guys. Sorry, endothermic reactions. Okay, not exothermic. It favors endothermic reaction, and especially if you have an endothermic reaction, then the values of Kc and Kp, it will increase. Okay? If you decrease the temperature, then what happens? Then it favors exothermic reaction. Now, for exothermic reaction, the values of Kc and Kp will decrease if you decrease the temperature. All right, everybody. Yes. Now you must be thinking, but ma'am, why are we studying about equilibrium constant or this chemical equilibrium or ionic equilibrium? Is it only because we have to appear for our IIT JEE and we have to sit for the exam? Is that why we are studying? No, Baba, no. Application of equilibrium constant is there. There are application. That is why we are studying. First of all, it can predict the extent of a reaction on the basis of its magnitude. Now, if you have a very large value of Kc, okay, if you have so much so that the power of the Kc is lying, either above 10 to the power 3 or maybe 10 to the power 3, that means that product formation will happen. That means that the equilibrium is going to strongly favor the product. The equilibrium wants the product formation to happen, okay. If you have a value which is between 10 to the power minus 3 and 10 to the power 3, that means that the reactants and the products are having, comparable concentration. Both of them have almost similar concentration. If you have a very small value that is smaller than 10 to the power minus 3, then it will strongly favor the reactant. That means the product formation will not be really will not be favored. The reaction would not want to go forward. The reaction would try to remain as it is. Are you getting it, everybody? It also can predict the direction of the reaction, everybody. Now here we come across another term which is called as reaction quotient. What is reaction quotient? Nothing. It is exactly the similar as, it is very similar to your equilibrium constant. Just that the equilibrium constant that you are measuring, you could measure it only at equilibrium. But what if we want to measure it at any other given time? Whenever the reaction is happening, if we want to measure it at that point of time, what will we do? At that point of time, we use the reaction quotient. Getting it? Getting it, everybody? Perhaps you have no doubt till here whatsoever, guys. See, QC is again same. Product of the products raised to the power their stoichiometric coefficient divided by product of the reactants raised to the power their stoichiometric coefficient or number of moles. Perhaps nobody has any doubt. Do you have any doubt, guys? Do you have any doubt? We will quickly finish this. After this, we have Le Chatelier's principle, and then we are almost done. After that, we're going to take a break, very small break of, if they have no power, that means if the stoichiometric coefficient is 1, then you let it be. Yes. For example, let's say that if you have a reaction where it is only written as, let's say, HI. Yes. If it is written as HI, then you are going to write KC. Yes. Or you are going to write QC. You are going to write QC is equal to just HI. That's it. That's it. You write. No power. You are not going to put any power on top of it. Okay. All right. Are we clear with this? Let's move forward, guys. Now the question is, ma'am, how to use the reaction quotient? Nothing. If you have QC and if you have KC, okay, if you have QC and if you have KC, and if QC is greater than KC, Babu, you're not understanding one thing. Chal, I'll explain this to you once again, okay? I'll explain this to you once again. Chal, let's try to understand this. Where were you? Where was it that we were? So, what I meant to say is, no, there is no QX and QP. There is only Q. There is only QC. Okay? Okay. Sanjay, try to understand. The reaction is going through equilibrium. The reaction will attain equilibrium at certain point. Let us say, just suppose, okay, A is a reactant, B is a reactant. I have mixed them up. And let us say that after 5 minutes, they will be in equilibrium. But before 5 minutes, if I want to calculate the quotient of the reaction, then before 5 minutes, at 3rd minute, at 4th minute, at 2nd minute, at that point of time, I will try to calculate QC, not KC. KC and QC are basically the same thing. It's just that KC you can only measure when the reaction has attained equilibrium. Once it has attained equilibrium, then you measure the equilibrium constant, that is KC. The reaction is going to, at that point of time, before attaining equilibrium, if you want to calculate something, then you will calculate reaction quotient. Getting it? Now do you understand? Anurag, Sanjay, Mahesh, Tanishka, Dhanush, everybody? Yes? Do we understand this? Do we understand this? Very good. Very good. Yes, very good. Okay. Now, so normally what happens, if you get a sum, right, you must be getting, they will give you the KC value also. So if the QC is greater than KC, then you can predict. You getting my point? So all this time we were talking about equilibrium pe aane pe this will happen, equilibrium once you have attained that will happen, equilibrium if that happens then it will happen. Yes, definitely. How can you predict if equilibrium is going to get happened? How can you predict if the reaction will move forward or if the reaction will move backward? That is also something that you want to know, right? Must have been a question in your head somewhere that, oh, okay, equilibrium. But what after that and before that? See, this is why we have the reaction quotient. So when you find that the reaction quotient is more than Kc, then the equilibrium constant, that means the reaction will move backwards. That means that the reaction has already gotten towards the product side, but it would want to move backward now. Getting my point? If QC is lesser than Kc, that means that the reaction has a chance to move forward. The reaction would want to form product and maybe try to attain equilibrium sometime. Getting it? Yes, very good. And if QC is equal to Kc, that means at that point of time, now you know that, oh, we have just attained equilibrium. Yes? Then you know that, this reaction has just attained equilibrium. So, any time you can calculate, any time the reaction is happening. Let's say that the reaction is happening for 20 hours. You can calculate it at 22nd hour, you can 20 hours, right? You can calculate it at 18th hour, 19th hour, 1st hour, 2nd hour, 3rd hour. And what if, let's say that at 10th hour the reaction attains equilibrium. At 10th hour you will see that QC and Kc are same. Before 10th hour, that is from 1st hour to 9th hour, you will see that, oh, the reaction is going to move backward. That means you will see that the QC is lesser than Kc. And after the 10th hour, from 11th hour to 20th hour, you will see that QC is greater than Kc. That means now the reaction wants to get back to the equilibrium. It would want to go backward. So perhaps everybody is clear with their concepts. Does anybody have any doubt here? Does anybody have any doubt here, guys? I'm somehow feeling a little uneasy, guys. I don't know, like feeling a little weak and little sleepy suddenly. I don't know. Maybe I should have had some food. Sort of hungry I am. All clear? No doubt? Okay. Now, here, see, bachos, if you remember that whenever I teach you chemical kinetics, I keep telling you that thermodynamics, equilibrium and chemical kinetics, these three chapters are very closely related, right? These three chapters, all the three of them, they tell us different things about the reaction. So obviously, we have just some time back only, you know, yeah, I feel like it, like suddenly fatigue is happening. Anyway, let us try to finish at least one chapter, then we will see if ionic equilibrium should be taken today or later on. Anyway, so you know that sometime back only we were talking about how chemical kinetics is related to chemical equilibrium, because we spoke about rate of reaction, we spoke about rate of forward reaction, rate of backward reaction. Right, we have spoken about all of these. We also spoke about law of mass action. We spoke about law of chemical equilibrium. Right, we have done this. But now you see, we are also somehow trying to relate Gibbs free energy and equilibrium, guys. Yes. What is Gibbs free energy? We all know that Gibbs free energy is basically the useful work that is done by a system. When do we use it? We use it for processes which are at 298 Kelvin, 1 atmospheric pressure, and when we know that it is converting reactants in their standard state to the products. Right, everybody? Yes, we know this, Gibbs free energy. But you must want to ask me that, ma'am, but what is the relationship? Why are we doing thermodynamics in this chapter? Hey Baba, relation is there. See, relation is there. There is a relationship between delta G naught and the equilibrium constant K. And what is it? It is that, you know, delta G naught is equal to minus RT ln of K. And if you want to convert natural log to log base 10, then what will you do? Minus 2.303 RT log of K. And here K can be Kc or Kp. Kp bole to equilibrium constant, that is related to pressure when you have gaseous reactants, gaseous product. And when you are talking about Kc, that means when we have equilibrium constant related to molar concentration. What can be the unit? Oh, there are different units, guys. If you have R, that is the gas constant, the universal gas constant, if it is in joule, delta G naught will be in joule. If you have universal gas constant in calories, delta G naught will also be in calories. But temperature, always in Kelvin. No changes there, everybody. Okay, no changes there. So here are some important formulas of delta G naught. This is also written. I will be sending you this notes, guys. Shall I send you this notes? These are all my handwritten notes, by the way. Shall I send you this notes? Do you want this notes? I can. I mean, it's all anywhere written. I just have to convert it to PDF and send it to you. So you tell me, should I collate the printed, the typed out notes as well as this, and together I should send it, or do you want just my handwritten notes and that will be okay? Whatever you want, you let me know in the chat box. I'll do that. Okay. So here are some formulas. Delta G naught is equal to minus RT ln of K. Ln of K, that means equilibrium constant can be figured out minus delta G naught divided by RT. Yes. And if you take anti-log on both sides, you will get K is equal to e to the power minus delta G naught divided by RT, and that's it. These three are very, very, very important. Send separately. Okay, I'll do it. Send separately. Okay. Yes, Mahesh, that we study in electrochemistry. That we study in electrochemistry, है ना? Okay. Now, if you have a spontaneous reaction, that means the reaction is happening apne aap se. The reaction is just happening on its own, right? Then what will happen? Delta G naught will be 0. Minus delta G naught divided by RT is going to be greater than 0. And K will also be greater than 0. Okay? And in this case, you will see that the reaction will proceed in the forward direction. And the products will be formed spontaneously. Predominantly, because the reaction is happening spontaneously. No, it does not require any energy. The moment you know that you have put the reactants and you have activated the reactant, just like we did yesterday, activation energy, everybody. Yes, you have activated the reactants. The reactants would want to become the product, and the products will be formed here predominantly. Okay? But if you have a non-spontaneous reaction, bachu, then what will happen? Check it out, everybody. One second, here. See, what did I say? Delta G naught lesser than 0 for spontaneous reaction. But if you have non-spontaneous reaction, delta G naught will be greater than 0. Delta G naught is greater than 0. Minus delta G naught divided by RT is going to be lesser than 0, and K will also be lesser than 0. In this case, the reaction will proceed for a very small extent. It will proceed towards the products, no doubt about it, but for a very small duration, and the concentration of the product that will be formed, it will also be tiny. Okay, very small it will be, not more at all. Okay, it will be very, very, very less, guys. Okay. Now, of course, we have not come towards equilibrium. We have not come towards ionic equilibrium yet. We still have to understand about what you call it, Le Chatelier's principle. Right? We still have to understand Le Chatelier's principle. But before we understand Le Chatelier's principle, guys, let us come to this part and tell me something, okay? Let us suppose that you have a reaction and the reaction is going on and on, but suddenly there is an external stress. Acha, what do you do? What do you do when you have, del G should always be negative for a reaction to occur, right? But bacha, you have spontaneous and non-spontaneous, isn't it? Spontaneous and non-spontaneous, isn't it? So for spontaneous reaction, where the reaction is happening on its own, then it is delta G naught lesser than 0. If you have non-spontaneous, delta G naught will be greater than 0. Okay? Correlate this once, Tanishka. Correlate this once. Okay? Your system needs break, kya? Nahi, pehle, let's finish this chapter, bacha. Let us finish this chapter. I don't want to, take a break here. Let us finish chemical equilibrium. After that, we will see, because even I am going through a lot of fatigue. So I don't know if I'll be able to complete ionic equilibrium. If not, I will record it and I'll send it to you. So by the next week, within the next week, you will get the ionic equilibrium also. Don't worry about it. But I am really feeling fatigued today. I don't know why. It's like I'm sweating, although the fan is switched on. I'm sweating, and my hands are also sweating. And I'm feeling very, Like I want to sit down. Feeling very tired. Anyway, no worries, no worries. Let us complete this. Okay? Yes, Lakshmi, 2-week challenge should be enough, but provided you are solving a lot of problems on your own. The concepts we are taking care, the problems also will be taking care of it tomorrow, but you will have to solve a lot of problems on your own. So guys, and let us understand this, okay? So we are here, we are studying. Suddenly, what if there is an external stress that is applied to you? What would you do? What would you do? Okay, let us take another example. Suppose everybody, after your 10th examination, from your 11th standard, you know that you guys, most of you are going to go for JEE. Some of you are going to go for NEET. You knew this, right? You knew this, correct? But even then, the moment you get a test, the moment a test is announced, don't you think that you suddenly start panicking, right? But some of you, only some of you, very few students who are really very chalu bro, very chalu. Yes, those chalu students, what will they do? Because they know that the test will be coming, they will make sure that they are not very tensed. Thank you so much, even, but I do not have coconut water. Yeah, I can only drink water. But anyway, no worries, guys. Guys, chill, everybody. It'll be fine. I can handle myself. Don't worry about it. If I feel really sick, I will stop the class. Okay? I'm feeling all right. I'm feeling a little, yes, I'm feeling a little not well, but I think I can handle right now. Okay? I can handle right now. Chill. Don't worry. If I feel too bad, then I will stop the class. Okay? Don't worry. So at that point of time, don't mind me. But I think I can handle it right now. I think till Chatelier's principle I can handle, but I don't know if I can take the class till 7 or 8 as we thought. Okay, I thought I'll be taking the ionic equilibrium till 8 o'clock. I don't know if I can stand here for another 2 hours. So let us try to complete at least what we can. Okay, chalo guys, come back here everybody. What would you do? Do you all want to just get into the panic mode? No. Some of you would also like to see that what can I do to reduce the stress? What can I do to reduce the stress? Collect some notes, go through some reference books, go through some previous year question. What are we doing? We know that a test is coming. To counteract all of these, we do something, isn't it? You know, similarly, a reaction goes through everybody. Just read the statement. If an external stress is applied to the system, which is in equilibrium, the equilibrium for that time, it will get disturbed. No worries about it. Yes, the equilibrium will be getting disturbed. But to reduce it, you know, what it will do is, it will try to counteract the effect of the change. It will try to counteract the effect of the change. Let's say, everybody, if I am chilling, okay? If I'm chilling, suppose I'm just chilling, and somebody just comes and tells me that, bro, you have to give the exam. I'll be like, there will be, in my mind, there will be a panic, but for some time, don't you go into that shock? You are like, huh? What exam? How exam? Kahan se aaya exam? I don't know. You will get into the shock, isn't it? Will you or will you not, guys? You will, right? What did you do? You were trying to counteract that effect of the change. You are like, suddenly, how come? What? No. Then you get into this, that acha, exam is coming. Now I have to take some action. Now I have to do something. Now I have to, do this. Now I have to do that. Then you will change. So yes, this is what is happening. Now, when we talk about stress for a reaction, what is the stress that we are talking about? Here, when we talk about a stress, we're talking about maybe a change in the concentration, maybe a change in the pressure, maybe a change in the volume, maybe a change in the temperature, or maybe the addition of an inert gas. Anurag, do you remember, Anurag? You asked me. Anurag, you had asked me, ma'am, how do we break that equilibrium, right? You did ask me, isn't it? Exactly. See what is happening. This is what happens here. Okay? This is what happens. Now let us understand that where can we apply the Le Chatelier's principle on chemical equilibrium? Change in the concentration. When you increase the concentration, what happens? The reactant, they favor the formation of product. Why so? Why so? Arey Baba, this is so simple, common sense. If you are adding more concentration of the reactant, if you are adding more reactant and more concentration, what is the work of the reactant? What do the reactants want to do? The reactants, they actually want to form products, right? So yes, the reaction will move in that direction where where it can consume the concentration of the reactant and be a little more stable and form a product. Are you guys understanding this or not, everybody? Suddenly what happened? Suddenly why everybody just went off? Anyway, next. See, increasing the concentration of the product. When you increase the concentration of the product, the reverse reaction will be, favored. The reverse reaction will be favored, and at this point, what will happen? More and more reactants will be formed. For example, the reaction that you had, okay? For example, let us say that the reaction that you had what? You had H2, you had H2 plus I2, and that was forming 2HI, everybody. So suddenly if you increase the concentration of H2 and I2, what will happen? The H2 and I2 together would like to form more product, more product, more product. But if you increase the concentration of 2HI, HI would like to see again what are they doing? They are trying to counteract the effect of the change here. Yes, the moment you have increased the concentration, they are like, no, Baba, but we did not want it. We want to attain equilibrium. So they would want to get consumed and form more products so that they can come into the equilibrium. Guys, am I making sense, everybody here? Are you getting it? Yes, are you getting it? See, I have just given you this example. Equilibrium here will be disturbed when you add hydrogen in the reaction mixture. And the reaction, when will it get restored? When will the, when will the reaction again be in equilibrium? When it has moved forward. So you tell me, guys, I understand that many of you right now, you know that second attempt of JEE is coming. Some of you are stressed. But what are you doing? To move forward, what are you doing? You are like, chal padh lete hain yaar. Let us just study and get over with it, because once you are done with the exam, then you can chill again. What is our usual equilibrium? Our equilibrium is this. We would like to all sit and chill, isn't it? Yes. Now what am I doing? I have disturbed my equilibrium by taking a class. Before this I was chilling. Now what do I want to do? I want to finish my class faster so that I can chill again. You see, getting it? Same analogy as your life, everybody. Same analogy. See? Getting it, everybody? Yes, guys? Yes? Now, everybody, moving on from here. See, effect of concentration. Let's take another experiment here. So, remember this example that I showed you in the beginning. So, you take Fe3 plus SCN minus, which is colorless. You mix it, you get a deep red color. Okay, a reddish color will appear when 2 drops of 0.002 molar potassium thiocyanate solution is added to 1 milliliter of 0.2 molar iron nitrate solution, and it forms FeSCN3 plus, okay, or FeSCN2 plus, FeSCN2 plus. So you will notice that the intensity of the red color becomes constant. The moment it attains equilibrium, you will get to see a red color. But then, now what you do is, if you add more reactant or a product, you will see that the intensity of the red color fades away. Nice example? Yes? Is it a nice example? So in accordance with Le Chatelier's principle, the concentration, that is stress, removed Fe3 plus is relieved by dissociation of this complex to recharge the Fe3 plus ion. What will it do? It will want to create more Fe3 plus ion so that it remains at that red color that it wants. Like we add extra reactant, we can add the product also. Yes, absolutely. Now let us understand that if we change the pressure, then what will happen? Guys, did you get this? Here what we were doing, we were understanding change in concentration, okay? Change in concentration is done. Now let's understand change in pressure. What will happen if we have change in pressure? If you increase the pressure, the volume decreases proportionally. Right, everybody? Do we all know this? What did we just know? We have known that PV is equal to nRT, right? That means P is equal to N by VRT. N by VRT. If pressure increases, volume decreases proportionally. Correct? So once again, according to Le Chatelier's principle, what will happen? The moment you increase the pressure, the equilibrium will shift. Why? Because the equilibrium has just received some stress. It does not want the stress. It will be like, no, adjust it. Here, what is happening? I want to adjust it. So what will it do? it will move towards that side wherever there is less gaseous moles in the reaction. Wherever there is less gaseous moles in the reaction. So my dear students, what will you do is, let's suppose that you have N2 plus you have 3H2 and you have it is going towards 2NH3. Am I right? Now if you increase the pressure, what will happen? It will try to form more products. Why? Number of moles this side is 2, number of moles this side is 1 plus 3 is equal to 4. Number of moles this side is more, 4 is more than 2. So what will happen? It will favor the formation of product. Guys, am I making sense, everybody? Now, if there is no change in the number of moles of gas, then a pressure change will not affect the equilibrium. If both the sides on the reactant and the product side, if you see that the number of moles are same, then the pressure change will not at all help with anything. Yes, got it? Yes, guys, clear? Yo, people, yes or no? See, again, I'm not receiving any yes or no, guys. This is not nice. See, another example I'll show you. Another example. See here what is happening. Here what is happening, you have again 3 plus 1, 4, right? You have 4 moles this side. Here you have 1 plus 1, that is 2 moles only this side. Here you have only 2 moles. Now if you double the pressure here, okay? The moment you double the pressure, what will happen? The equilibrium will shift and it will try to move forward direction. Why? Because the number of moles of the gas this side is less. That means the pressure is decreased here. That is why it will move forward. Now, do you realize, everybody, that age-old concept that we learned when we were very young, remember, wind current and pressure, that always from higher pressure to lower pressure it will come. Do you see how it is applying here as well, everyone? Do you notice, guys, how it is applied here as well? The moment you see that the number of moles this side is more, number of moles that side is less, that means that the pressure must be less that side. Hence, it is trying to move forward. See, higher pressure to lower pressure again. And that is why, everyone, I do not know how many of you have ever thought, but your foundation classes are so important. We do not pay attention. We think that all the JEE and NEET, we will, four dunga, we will, we will rock the exam when we get there. But your foundation is so important that the same age-old concept that you learn when we are chottu, that is what you are still studying today. Nothing. It's just a fancier name, Le Chatelier's principle, change in pressure, high pressure to low pressure only. That is what is happening. Anyway, moving on. If we change the temperature, then what is happening? When you increase the temperature, it favors the direction which absorbs heat. Are obviously, Baba? Are obviously? Why do you think you are able to cook? Why do you think you are able to cook, guys? What are you doing? You are giving the heat, isn't it? And what is the dal doing? The dal is like, yeah, allow, more heat. Yes, bring it on. I will be cooked. Yes. So increase the temperature. It will favor the direction where it can absorb more heat. And at certain point, your dal has become jal gaya. Correct? But if it is an endothermic process, if it is an endothermic reaction, higher temperature will promote the forward reaction. Same example, guys. Endothermic process is basically cooking. So when you are cooking, when you are applying heat, what is happening? Your cooking becomes wet. Right? Right, guys? But if it is an exothermic reaction, higher temperature will promote the reverse reaction, because exothermic likes to release heat and not absorb heat. Yes? Clear here, everybody? Okay. Now, what if we want to add an inert gas? Inert gas, it depends on whether the volume is allowed to change or not. Okay. If the volume is constant, you are not allowing the volume to change at all. Then if you add inert gas, it will increase the total pressure, but it will not affect the concentration. That means it has no effect on equilibrium. Are you guys getting it? But if it is constant pressure, then if you add an inert gas, it will increase the total volume, which will decrease the number of moles per unit volume, everybody, that means that equilibrium will shift and it will increase the number of moles of gases. Guys, am I clear, everyone? Am I clear, guys? Yes, everybody. And last but not the least, we have effect of catalyst. So a catalyst increases the rate of the chemical reaction. What does it do? It makes available a new energy pathway. It makes a shorter pathway. That means that what is happening? Shorter pathway bole to everybody where the energy is less. You all know that in the nature, the system always wants lesser energy. Lesser energy means very stable. So yes, when it has a low energy, it moves faster and it moves it wants to complete itself faster, everybody. So by making available a new low energy pathway for the conversion of reactant to products, that is exactly what we have in effect of catalyst. If it increases the rate of the forward and the reverse reaction, guys, please understand that a catalyst will not only increase the rate of the forward reaction, but it will also increase the rate of the backward reaction. That means that it will pass through the same transition state and it will not affect the equilibrium. From the very beginning only we were talking about this, that catalyst does not affect. So Chatelier has just made it even more, more explanatory. So I guess with this note we are done with Chatelier's principle. Is there anything else that we have missed out on? Mostly we are done with everything. Rest, whatever is remaining, a little bit maybe is remaining. I don't think so anything is remaining. Is there something remaining, everybody? I don't think so. In chemical equilibrium, what do we have? Chatellier's principle, addition of inert gas, effect of temperature, solubility of substances. No, that I have. That is exothermic and endothermic, right? We have done effect of change in pressure. Yes, we are done with this. Okay. That is it. Important point about equilibrium constant done. Yes. And there is one thing for degree of dissociation, which is basically the same, exactly the same as you have studied the degree of dissociation. But chalo, let me still just show it to you once. Where is it? Don't have it here, huh? Yes, Karthikeyan, you can definitely try, bacha. You can definitely try, hai na? Here is degree of dissociation. So, bacha party, everybody, we all know that what is degree of dissociation? We all know the degree of dissociation is alpha. What is it? How do you define it? You define it as the fraction of 1 mole of substance which is dissociating into products, right? Acha, when we come to ionic equilibrium, we will also have to learn what is ionization and dissociation, guys. So here it is fine that dissociation, we know that we are taking 1 mole of a substance which is dissociating. That means it is breaking down into its products, right? Yes, okay. And it is defined for 1 mole of a substance. Suppose you have 5 moles of PCl, PCl5, okay, and 2 moles of PCl3 is dissociated. I showed you the example, do you remember? PCl5 will form PCl3 plus Cl2, yes. So here alpha will be 2 by 5, guys, 2 by 5. That means degree of dissociation is basically the amount of reactant that is dissociated at equilibrium if we start with 1 mole of the reactant. Once again, easy peasy biryani tasty. Anything more that you want? But how can you write it, everyone? Number of moles dissociated at equilibrium divided by initial number of moles that you had taken. So what did we do? See, number of moles dissociated was 2. Initial moles, how much did you had? Initial moles you had 5. So 2 by 5. Clear? And what is a percentage? Multiplied with 100. So here also nothing that we have missed out on. Okay? So all of these things will reach to you, everyone. All of these things, it will reach to you, everybody. I think today we will have to finish, but let me take you through at least 1 to 3 questions here. Let me take you through at least 1 or 2 questions. Yeah, it will not be very nice if I don't take you through one question. Shall we solve some questions? 1 or 2 questions, just 1 or 2 questions. After that, I'll finish it, guys. Okay? After that, I'll finish it. I'll do equilibrium, ionic equilibrium later on, and I will ask our channel manager, that is Pradeep sir, to change the thumbnail, and I'll ask him to make it just chemical equilibrium. Okay? We will do ionic equilibrium later on. So in 2 hours, bacha party, everything is crystal clear. Nothing we have left. We have completed the whole chapter of chemical equilibrium, degree of dissociation to Le Chatelier's principle to different types of reactions to everything from the scratch to your advanced, basics to advanced, everything is clear. Any question that comes from this chapter, I suppose you will be able to do it, okay? But my telegram, same name, Nabamita, and many students, they call me Nobita. So you can either search with Nabamita Bhattacharji or Nabamita Nobita, you will find me. I think I'm wearing a purple color shirt and there is a, and there is a blue color background, sort of like that. Or you can find a telegram channel where probably I'm wearing a sari or something like that. So I think that's what it is. Okay? Search me. I do not know because I hardly open all of these things. So just check it out. Chalo guys, let us solve this question. The formation of ammonia from its constituent elements in an exothermic reaction. The effect of increase in temperature on the reaction. Guys, exothermic reaction. We have just done it. If it is exothermic reaction, then the reaction will proceed toward backward reaction. Yes, so that means just the moment we read the question, I think we will be able to understand, isn't it? Yes, it will be option D. It will move towards backward. Haven't we just studied? If what Le Chatelier's principle, everybody, if there is an exothermic reaction, what will happen? In an exothermic reaction, you will see that the reaction is moving towards backward. You were waiting for ionic. I'm so sorry, bacha. I really want to take it, but I don't think I'll be able to stand for another 2 hours because I am feeling very fatigued. I'm feeling very weak, seriously. Like somehow my hands are sweating. Every time I'm keeping my hand on the table, there is sweat droplets. And I'm feeling a little weak. So I would like to sit down a little, take a rest. But I promise it will come, yeah. It will come. Ionic equilibrium will come very soon. In fact, if I can, by this Sunday, Monday, Tuesday, give me 3 days. If I can, by tomorrow, if I can record it, I will send it to you recorded. Because anyway, coordination and DNF block I'll be recording. And it will come to you on Sunday. DNF will come on Sunday. And on Tuesday, coordination will come. I will try to record ionic equilibrium. Recorded will be even better for you because no chat or anything. Will you all be able to study from recorded session? Tomorrow, if I'm feeling fine, right in the morning, I'll record and give it to Pradeep sir. He will publish it. Is that okay, guys? Is that okay? I'm so sorry. I'm not feeling a little well. Otherwise, I would have taken it. Pakka promise. Pakka promise. I would have taken it. I actually have the notes also. It's not like I don't have. See, solubility, product, solubility. I have the notes also. But I don't think that I can stand for so long. But it will be too difficult for me. And if I have to sit also, I'll have to, arrange the camera settings. I'll have to arrange the green screen settings and then I'll have to sit. So it's just not doable right now. That is why. Okay? Will you all be able to read? Everybody, you will follow the recorded session, no? Later on, I will not see that if I have not taken a live session, you will not watch the recorded session. It's not going to be like that, no? Then tomorrow, pakka, I'll record and send it to you. Pakka, I will record and send it to you. I will record DNF and coordination chemistry in the night, and this ionic equilibrium I'll record in the morning and I'll give it to Pradeep sir. Okay? Chalega for everybody? Works? Pakka works, no? Pakka promise all of you are going to watch it? All the students? Yes? Thank you so much. Chalo, one more question that let's do it. One more question then let's do it. The pH or we cannot do this because this is a ionic equilibrium question. Yeah, this is an ionic equilibrium question. Chalo guys, I think you know what, let us finish the session here today. Okay, extremely sorry for this abrupt end. Let us finish the session here today. I'll be giving you this notes. Okay, I'll be giving you this notes. See, all of these are here also. These are all your cheat sheet, guys. All of these are your cheat sheet. You can go through this. I'll be sending you this notes in the Telegram channel. Yes. And Sunday DNF, Monday coordination, or Sunday we will do ionic equilibrium, then Monday DNF, and Tuesday we will do coordination. Okay, so these 3 chapters will be coming up. Please do not forget your 2-week challenge, guys. We are taking a lot of pain and we are trying to complete it. This is a lot of effort. You must follow these efforts, everybody. Okay? Today, I hope your concepts is clear. Tomorrow, we are going to do 35 to 40 questions in chemistry just for physical and inorganic. Be there in tomorrow's session. It's going to be a long marathon. All of us are going to, keep coming one by one, everyone. So be there. I'll see you tomorrow. All the very best. Study well till that time. You will get the notes. Okay. Tata, bye-bye, everybody. See you all, and I'll see you tomorrow. Bye-bye. And stay tuned to the channel. Do not forget to like, share, and subscribe with your friends.